Alrighty, next slide, please. Alrighty, Brian.
Sorry, I'm muted. While we're talking temp comp, there was another question here, Jacob, and it was temperature compensation appears to assume the entire load cell is at a constant temperature. Is that accurate? Yes, that's fair and accurate. There is temperature compensation performed in a specific area on every load cell in terms of where we can get to it in the manufacturing process after we complete the bridge. So if you were to have two scenarios, one being very localized thermal changes, that can impact the load cell's ability to respond properly from a temperature compensation standpoint. Or if you have the scenario where you have a thermal gradient being introduced, say, through the load string, that may take time for, again, if the load cell doesn't stabilize thermally, then yes, you could have some less than complete thermal compensation happening from a bridge standpoint. So just for reference, if it's an LP we're talking about, most of our thermal compensation is going to be done for the zero balance, at least behind our label. So pay attention to that. You don't want to have anything hot shooting right at our label. That's not going to allow the thermal comp to work as best it can. So Jake, were you going to say something?
No, just great question. Yeah.
All right, so the last aspect to keep in mind when we're talking, performance and accuracy is calibration. So, we've talked about designing a good sensor, choosing the right design considerations, building it as accurately as we can, doing some manufacturing tweaks during the process to optimize performance. And the last part of it comes down to calibration. And you can have a spec sheet on a product, and that's how it performs. But in terms of actually getting unit accuracy, unit confidence, in terms of how closely is this measuring 5,000 pounds or 5 kilonewtons, right? The calibration plays a big role. So not only does it obviously verify hysteresis, nonlinearity, all of our specifications that we check for, but the uncertainty around that in terms of the uncertainty of the cal then really plays a big role in, okay, how tight confidence can you have in your test setup? So that's going to come down to the standards that are being used, the traceability on those standards, the stated uncertainty. We're A2LA accredited. We have our Spielberg accreditation on our website. Tells you the uncertainties there for the different force ranges. We do dead weight cal up to, I believe, 1,100, 1,200 pounds, somewhere in there, Jacob. And then from there, we go to hydraulic reference standard cal, which is what's depicted here, where we're using a couple load cells to track. So in that schematic there, we have a load frame. That top unit would be the DUT, or the unit being calibrated. The unit below that would typically be our calibration standard, where we have very high confidence in that. That goes back to NIST for calibration. Some of our standards in our lab are older than 40 years, believe it or not. So we have binders and binders of history and extreme confidence in those standards. And then depicted under that would be the hydraulic control sensor for the hydraulic frame. So that one would be controlling the actuator to monitor the applied force. So this is a good depiction here. Question just came up: do we sell calibration frames? Yes, we do. We sell essentially what we use every day, and these are cal frames that have to provide 0.04% uncertainty and still do it quickly and efficiently enough to ship out 60, 80,000 sensors a year. So we absolutely do offer a couple of different models, Andrew. We can get you in touch with some information there. So not only does the uncertainty and the standards and what you're using play a role, but there's also what is the specific calibration you're having done. So depending on the sensor, it may come with a tension-only cal, it may come with a compression-only cal, it may come with a universal tension and compression cal. But then also you can keep in mind that if you have a very specific test where you really need ultimate precision, there are options such as asking for specific cal points, where we will actually go and hit that exact point, which is going to drop, linearity, hysteresis. Most of that stuff probably won't matter anymore. Maybe hysteresis, I guess, if you're cycling. But again, you can get better uncertainty through your calibration. We recommend that if you have the ability to calibrate in-house, right, that you calibrate in situ as much as possible, or using fixtures that you would use in your setup. We do have some customers that have us calibrate their unique models using replication of their fixturing, for example. So that's an option. And then we have options such as ASTM 74 cals, which we do on all of our calibration grade sensors. But these will allow multi-point runs and give you lower load limit values, as well as coefficient equations, which, depending on your instrumentation, you can essentially, through software, remove all nonlinearity concerns, right? And really get exactly where that load would be. So, all right, next slide.